A physics lab group is given a spring that can be both stretched and compressed, as well as a set of masses. They are asked to use the masses in conjunction with the spring to determine its spring constant using two different methods, and then compare the results. So in part A, they're going to hang the spring vertically and that's going to cause the spring to stretch by a distance x from its rest length. So each m will lead to a different value for x. So we need to come up with an equation that relates the m with the x. And we can do that by drawing a free body diagram for the mass. Because on this mass, you have two forces on it. The downward gravitational force and the upward spring force. And because the mass isn't moving, we can use Newton's first law, which tells you the upward force is equal to the downward force. So if I set them equal, Fg equals Fs, and again, that's because of Newton's first law, the net force in the y direction equals 0. When you plug in some equations, you get mg is equal to kx. So this is a nice simple equation that relates the m with the x for a specific constant value of gravity and a specific spring constant that we are trying to solve for. So I can take this equation and linearize it. Now technically there are multiple ways to solve this problem. Like I could take this equation and solve it to get m by itself. So you have m is equal to kx over g. I could linearize that equation if I wanted to, but I'm just going to stick with linearizing this equation. So I'm going to compare this equation with y is equal to mx plus b. Instead of putting the m, though, I'm going to make it the s for slope, because I don't want that m to get confused with this m. And there's no plus b in the mg equals kx. There's no plus sign, so I can just ignore this plus b and just compare the left side of the equation, the y, with this, and the right side of the equation with this. And that'll help me figure out what I should plot on both the vertical axis and on the horizontal axis in order to linearize the graph. If I look at the left side of the equation, on the y-axis, I could actually plot m times g. I could take each of the values for m and multiply each of them by 9.8, and that would give you something to put on that vertical axis. Now, mg is a force, so it's measured in newtons, but keep in mind the masses on this table are measured in grams, so you'd first have to convert them to kilograms, divide them all by 1,000, and then multiply by the 9.8. And you can use that top blank row in the table to fill in all the different values for m times g. So like, for example, the first one you get, the 50 grams, when you divide 50 by 1,000, you get 0.05 kilograms, multiply that by 9.8, and you'll get an answer of 0.49. So that first box above the 50 would be 0.49 newtons. On the x-axis, you could simply plot the x, the stretch distance of the spring. That is measured in the standard units of meters. Notice in the table that it's given in centimeters, so you're going to have to divide them all by 100 to properly convert them, and you can fill in those values in the bottom row of the table if you want. So like the first one, under the 1.2 centimeters, you would just write that as 0.012 meters. So once you've got those two things picked out, you can go ahead and fill in the rest of the table and then plot the data points. If everything is done properly, you should have 6 points that are relatively linear. The last one's going to be a little farther away from the rest of them. And remember, the way you do a linearization problem is you want to draw a best fit straight line that just passes through all the points. You don't want to connect any of the points together. You just want to draw the perfectly straight best fit line, and then you want to find the slope of that line by picking 2 points that lie on the line. Do not pick 2 of your data points. People are still doing this on the test, and you cannot do that. Pick a point on this far end of the line and pick a point on this lower end of the line. Hopefully the line passes through 0, 0, the origin, so you can pick that as one of your points, and pick the upper point, and from that you can calculate your slope. And then notice in this case, if I go back to the equation comparison, that the slope of the line is simply equal to the spring constant because of that part right there. So whatever slope you get for this line, if you plotted mg versus x and you convert all the units properly, that slope is your spring constant, and the answer to this problem works out to roughly around 40 newtons per meter. Let's go on to part B. In the second method, they're going to attach the spring horizontally to a wall that's just above a frictionless surface. So if we draw this out, we have the spring attached to the wall above the frictionless surface, and that's going to be connected to a mass that is oscillating back and forth on the surface. And this time, instead of measuring the stretch distance, you're going to just set it into oscillatory motion and measure the period. And the equation that relates period with mass for a mass spring system is one of the ones straight from your notes. T is equal to 2 pi times the square root of m over k. So there's no need to derive the equation this time like we did last time. Last time we had to come up with the equation by drawing a free body diagram. This time the equation that relates period and mass is already known. So if you want to plot this equation, if you match this equation with the y equals mx plus b, or y equals sx, and I'm not going to put the plus b on there, you can see that on the y-axis, you should plot the period. On the x-axis, now remember, it's the period and the mass are the two variables that are changing, so those need to be part of the x and y-axis. So on the y-axis, you've got the period. On the x-axis, you should have the mass, but notice that mass is under a square root sign. So on the horizontal axis, you should be plotting the square root of m. So in the data table, you can take each of those values of m, convert them first into kilograms, and then once you've got them in kilograms, take the square root of all those numbers. So like for the first one, you have 50 grams, that is 0.05 kilograms, and if you take the square root of 0.05, you'll get a number that's about roughly 0.22, and that has units of kilograms to the 1/2 power, or square root kilograms. And then you can see that by plotting t on the y-axis and square root of m on the x-axis, what's left in this equation, the slope of the graph, is 2 pi over the square root of k, because k is in the denominator and it's still under a square root sign. So the slope is 2 pi divided by root k. So when you plot those points on t versus square root of m, you should get another set of points that make a roughly straight line. When you draw your best fit line, that's going to be your slope. So you just rearrange this equation to get k by itself and plug in the value of the slope, and you should get the similar answer to what you got on the front side of the page, around 40 newtons per meter. Notice another way you can solve this equation, another way you could linearize this that may be slightly easier, is if you took that original equation, what happens if you just square both sides of the equation? You get t squared is equal to, now 2 pi squared becomes 4 pi squared, and for the m over k part, you just get rid of the square root sign, so you have 4 pi squared m over k, and if you match this to y equals sx, then on the y-axis, you could plot t squared. So you'd have to take each of those values for t and just square them. And then on the x-axis, you could just plot the mass. No need to take the square root of the mass this time, but you just have to convert it into the proper units of kilograms. And then what you're left with is all the rest of this stuff, 4 pi squared over k. So s equals 4 pi squared divided by k. And when you get the value for the slope for this set, you would just rearrange the equation to get the k by itself. And that should give you the same value of roughly 40 newtons per meter. And finally, in part C, calculate the percent difference, I just want to make sure that everybody is clear when to use a percent difference versus when to use a percent error formula and what the formulas are. For percent error, if you have a known value, that's when you use percent error, and the formula is the experimental value that you calculated minus the theoretical or the known value. Take the absolute value of that and divide it by that theoretical value and then multiply by 100. So that's like, for example, if you wanted to use the pendulum formula to figure out Earth's gravity, where you know the true value of Earth's gravity, you know the g, so that would be your theoretical value. So E minus the experimental value minus the theoretical value divided by that theoretical value would give you a percent error. Now, if you don't know what the value is, like in this problem, we don't really know what the value of the spring constant is. We're just coming up with two different experimental values. That's when you use the formula for percent difference. And the formula for percent difference, you have two experimental values, which we call E1 and E2. You just subtract them and take the absolute value, and you divide it by the average of those two values, and then multiply that by 100. So in this case, let's say, for example, that we get maybe like 39 newtons per meter for part A, and then we get 43 newtons per meter for part B. First, get the average of those two numbers. You get the average by adding them and dividing by 2, which in that case would be 41. That's the number that would go down the bottom. And then you just subtract those two experimental values in the numerator, taking the absolute value of them. So that would just be 4. So it'd be 4 divided by 41, and then times that by 100. That gives you the percent difference. So remember, use percent error if you know the true value of something, and that's the t, the true or the theoretical value. Use the percent difference if you don't know the true value of it, but you come up with two different experimental ways of finding it.